All right, welcome everyone. Thanks for joining our Tech Talk today with the Tech Academy. I'm Regina, by the way, and today we have Dr. Brent Wilson, who's a professor of computer science at George Fox University, and they're going to talk about the importance of algorithms. So thank you for being here, Doctor, and take it away.
You're welcome. Glad to be here. Well, welcome everyone. And it's been a while since I've had an opportunity to join you on a Friday afternoon, so I'm looking forward to it today. What we're going to do is sort of dive into, it's a relatively technical topic, but we're going to stay pretty high level. We're going to look at it really more from a perspective of those that are sort of just beginning their careers or are thinking of beginning their careers into this field of development. And so for those that are current students or even those that are prospective that are just sort of checking it out, I think you'll find quite a bit here today that is definitely attainable and give you something to be thinking about as you go down this road. So when we think about software development, actually, let me back that up. Instead of think of software development, just think of software usage, right? All of us use software every day. We're using it right now. And there are multiple times, probably every day, every one of us at some point goes, oh, my computer isn't acting like it should, or, this is too slow, or, why is it taking so long for this to happen, et cetera, et cetera. And there's a lot of different reasons for that, from hardware type reasons to software type reasons. And what we're going to look at today is a little bit more on the software side. It's a little bit on the developer side to ensure as a software developer, you're not mistakenly making the software slower than it should be. And that's sort of our intent. So with that, let's jump in. So the first thing I would ask you, make sure I get the right window active. There we go. So the first thing I would ask you is, let's just play a little game. Simple game. Probably something you've done with your kids or nieces and nephews, right? I'm thinking about a number between 1 and 100 inclusive. When you guess the number, I'll tell you. Now, we don't have to play it as far as people start throwing numbers into the chat window, but you can think about it, right? Think about what number would you guess? I'm going to go out on a limb and say the vast majority of everybody in this chat, probably their first guess is going to be 50, right? And or somewhere close to that. Where if you think about how would a 4-year-old play, right? A 4-year-old is going to go 3, 72, 51, 63, 13. It's going to be like a shotgun approach, right? They're just all over the place. What makes your choice different and or better than what the 4-year-old chooses, right? It comes down to algorithms. It comes down to understanding a faster way to get to a solution, right? And so in this game, if you think about the 4-year-old, they would sort of check every number randomly. And so worst case, it's going to take them 100 guesses to get it, right? Best case, they could pull it off with a single guess. Probably not. So on average, they're going to have around 50 guesses. Yet, everyone in here that said 50 in your mind, you would probably get it in at most 7 guesses. And the reason for that is that you're going to be cutting this in half, right? You're going to take 100, and in your first guess, you have a new data set of 50. And in your second guess, you have a new data set of 25. And you're going to continue to have it over and over and over. And so worst case, you're going to do 7 guesses, because 2 to the 7th, because you're cutting it. This is a base 2 problem. By cutting it in half, you could guess, instead of saying 1 to 100, I could have 1 up to 127, technically, and you could guess it within 7 guesses. So that's worst case. Best case, same thing. You could get really lucky, in which case, go get a lottery ticket. Remember me. But on average, probably around 6.5, 6.2 guesses is probably what you're going to do, which is amazingly different than 50, right? That's a huge increase in performance, right? So let's just talk a little bit about some of this mathematics. So we're going to get just a little mathy for just a moment, and then we'll get out of there. So I got to take you back to high school math for just a brief moment and try to remember logarithms. Logarithms, when we write something like log base x of y equals n, what that really means is we're looking for a number where x raised to the power of n is going to be equal to y. In mathematics, when we write log of n, we're talking about log base 10 because we work in a base 10 system, right? Our money's base 10, any type we're adding, subtracting numbers, any type of numbers we're using is typically a base 10. But in computer sciences and software and technology, we use a base 2 system. We use a binary system. And so when we talk about log n, we're talking about log base 2 of n. Now, we're not going to do any problems with those, but just sort of throwing those out. I want to show you how they apply to the problem that we just did. When we did the guessing game with 100 numbers, what we're saying is, okay, the log base 2 of 100 is what? And if we can find that number, that tells us the maximum number of guesses that we would have to make. So in this case, the maximum amount of guesses is going to be, again, 2 to the x has got to be bigger than 100. We already found it. It's 7, 2 to the 7th. So log base 2 of 100 is 7-ish. We're going to leave all the decimals out for right now. But it's just a real quick way to evaluate things, okay? So now, if we look at a new problem, let's say we have a pet moving problem, okay? Pet moving company. Eric and Jack have diversified the Tech Academy, and we're now going to be pet movers. And they saw a need for assisting families relocating because of new programming careers. They researched and showed that families typically have about 2 pets, a couple cats or dogs, an occasional hamster or small reptile. How would you price such a service? Now, you don't have to type in, well, I would charge $3 for the first animal or whatever. But just in your mind, you could think about it. Well, probably, would you charge on a per animal basis? Maybe charge just a flat rate. I'll charge you $40 to move your pets, whatever the case. If I walked into the shop and I said, I have 2 pets, right? Probably say, okay, well, that would be $45. I said, well, here's what my pets are. My first pet is a goldfish. You're like, yeah, no problem. Piece of cake. Oh, yeah, I forgot to tell you. My second pet's an elephant. Now, all of a sudden, things change and change significantly. In fact, when I really need to think about moving these 2 pets, the goldfish plus the elephant is really just the elephant. Because the goldfish doesn't matter anymore. Put it in a jar, put it in the front seat, you're good to go, right? It's the elephant that's going to be the cost driver in this type of having to move 2 pets. This concept is what we call algorithm analysis, or Big O. Big O notation is really looking at algorithms to decide what's the elephant and what's the goldfish, what matters and what doesn't, right? So mathematically, let's just take a look at some polynomials for a moment. So here are some polynomials. Anytime in software, when we develop a particular algorithm, you're able to mathematically determine sort of the cost. And cost is typically defined as maybe CPU cycles or seconds. How many seconds does it take to complete that processing? So let's say here are 3 different algorithms of some sort. The first one is a function, and we have n plus 8. And you look at that and go, well, as n gets really, really, really big, n plus 8 is really just n, right? As n goes towards infinity, think of the data. As you start getting, if you're dealing with 2 pieces of data, then the 8 is going to have a big impact. But if you're dealing with a terabyte of data, that 8, whatever, it's a little mosquito. It doesn't even impact the problem. So the elephant becomes the n, the goldfish becomes the 8. And so we would say that this has a big O notation of n, okay? Look at the next one. The next one is actually a quadratic. We have n squared minus 3n plus 100. As n gets really, really, really big, n squared is going to get massive. Now 3n is going to get pretty big too, but compared to n squared, take 1,000,000. 1,000,000 squared, right? So that's 1 with 12 zeros. That's far bigger than just 3 million. 3 million is, it's just change, right? And so in this case, the elephant really becomes the n squared. That's what's going to be costly. The rest of it, not so much. The plus 100, you don't even notice that. And then the last one, if I had a function that was literally just 1, whatever I did, I just needed 1 CPU cycle, no matter how big the data, then there's no elephant. It's really only a goldfish. Now, this might seem really silly, but what we want to do today is I'm going to actually demonstrate for you algorithms which solve a particular problem. Now, we're going to take a problem. I've already developed code 4 different solutions to the exact same problem. And what we're going to do is we're going to actually run them and look at them and say, well, which is more efficient? Because at the end of the day, ladies and gentlemen, the difference between a sort of green beginning programmer and a seasoned programmer is that a beginning programmer tends to look for any solution, and a seasoned programmer tends to look for the best solution. Now, there's nothing wrong with looking for any solution when you're starting out, but you need to develop your skills and develop your knowledge so over time you find multiple solutions. Here's a great example before we go further. I have a friend who is a hiring manager at Microsoft at their world headquarters up in Washington. And he hires software engineers all the time. And one of his favorite interview questions is this. He asks them, he says, here's a scenario. You walk into a library and you're looking for a book. You go to the card catalog, you look it up. Okay, I just dated ourselves, card catalog. Anyway, you go to wherever you need to go and you look up where the book is. You go in the library to that place and the book is not there. But the library guarantees you that it's in the library, so it's been misshelved. How would you find it? Go. He says most folks can come up with 2, 3, 4 different ways. A pretty good problem solver might come up with 10. He goes, I'm looking for the person who can give me 30 different ways to find that book. Right? Solve the problem. How many different ways can you come up with? Now, they might all, a lot of them may be really, really poor, but the point is exhaust the space, and then you can do some analysis on what is good, what is better, what is best. And that's sort of what the whole presentation is today, is to be thinking about those things. So with that, let's take a look at some big O comparisons. So these graphs, and again, you don't have to necessarily know exactly everything you don't even have to read the numbers. What I want you to see is we have different lines. Some are much more gradual, almost. We have one that's like a flat line. We have one that's the green is just a nice, gentle, gradual increase. And then they start going up and up. And next thing you know, you have like exponential. Think of the horizontal as the amount of data that you're working with. So the more data you move to the right, and the vertical represents the amount of time it takes for your computer to finish that task, whatever it may be. So on the green line, I could have a lot of data, and it's probably going to finish pretty quickly. On the blue line, that's literally just takes off horizontal or vertical, I can't have any amount of data, or too much time. It's going to take way too much time to complete. This type of comparison, when you look at a variety of algorithms tend to fall into these 7 categories, these 7 lines that you have here. We are always striving for ones down that are as flat and horizontal as possible. Unfortunately, there are times you have to accept one of those that's more of a vertical climb, and that's hard, especially if you're dealing with a lot of data. So I hope this is all making sense up to this point. Let's see here. Oh, that is an exponential. Yes. If you don't mind, I would gladly take that question if maybe afterwards, if you want to follow up or something. It would get real mathy real quick, and I'm not necessarily want to go down that road if you don't mind. Yeah, okay, Mathy. All right. So let's take now. Where did there we go. All right. So let's do some algorithms. Let's say you have 8 identical looking coins, but you know one of them is fake. All right, and it weighs slightly less than the rest. What is the minimum number of weighings that you have to make to find the fake coin? Well, let's talk about a couple different algorithms. Hopefully everybody's thinking through in their head real quick how they might do that. Here is one that has a big O notation of N, and meaning if I have 8 coins, I can do roughly 8 weighings, right? I could take the first coin and put it on one of the scales, and I could weigh the second, and then I could weigh the third, and then I could weigh the fourth, and I could weigh each individual coin against the one that I chose. Now, will I find it? Absolutely. But it's going to take technically 7 weighings, but I could get there. There are ways that we can do this much quicker. So what about something like what's considered a logarithm algorithm? Is there a way that we can cut the data size down instead of 8 coins, right? What if we put 4 on each side? That's 1 weighing. Exactly. We can half it, just like the pick a number between 1 and 100. I can break it up in 4, then take the 4 and split it to 2, then take the 2 and split it to 1 and 1. I can do it in 3 weighings, right? 2 to the third is 8. That was a logarithm algorithm. Okay, it's a way in which you were able to cut that. Now, let's look at another problem. What about Oh, actually, we just went over this. What's your minimum, right? We did it in 3. An N solution, we talked about think of it as walking through every one of the coins. A log N solution was being able to cut your data size in half. What if we changed it to 9 coins? Now that sort of changes this a little bit. I could still do an N solution because I could take 1 coin and then weigh it against each individual 8 remaining coins. Is there a way that I could cut this, right? So think about what's the most, how many weighings would you need? This would be a chance if you are at a keyboard and you want to type in, what would you say for how many, what's the minimum number that you could get? Four? Anybody else? 3? Excellent. I can do it in 2. Think about that. Here's how I would do it. Instead of a log base 2, I'm going to go with a log. Excellent, Sherry. I'm going to go with a log base 3. What if I took my coins and I split them up into 3 groups of 3? I pick 2 of the groups, 3 and 3, and I weigh them. If they're equal, I know it's in the last group. All I need to do is pick 2 of the coins out of those 3 and weigh it. If they're equal, it's the coin left out. If it's not, it's whichever one is less. If my original weights are not equal, I do the exact same thing. I take those 3 coins, put 1 aside, and weigh. So you can do it in 2 in this example. Now, you guys are getting the sense for, some folks said 4. I came up with 2. The improvement there, hundreds of % improvement, right? Cut it in half. And so those are things you think about when we look at algorithm analysis. So we're going to run some code. Let's look at this problem. Let's say you have 2 strings, right? So just a whole bunch of letters. Can you tell if they are anagrams? Now, an anagram is 2 words that use the exact same letters, but they could be shuffled around. As an example, Python and Typhon. Not that they have to be words, just strings, and they're made up of the same, right? So you look at that and you think, how could you solve that? Well, there are a number of different ways. I solved it 4 different ways, and we're going to look at those, and we're going to look at the performance of those, and then we'll get a feel for, okay, algorithms matter. So with that, let me, here we go. Demo, discuss. Let me change the window. All right. So we'll stop, and I will reshare this window. All right. As soon as that comes up. All right. So we're not going to dive into code. We're not going to do any of that. We're really looking at performance stuff here, okay? So I've written a program in Python, which, by the way, I'd be more than happy to make available. So along with my slides, you can have the Python code so that you could be looking at it. So let me start running this program. All right. So it comes up, do I want to enter via the keyboard or read in from a file? Because I have some files we're going to read in and we're going to test. We'll just start with the keyboard. So I want to read in from the keyboard, and it failed. What in the world? Nice job, Wilson. What just happened? This is absolutely hilarious. I have not changed this code forever. Let me quickly make sure I'm using the right one. Yep, anagram. Oh, I know. Python 3. Oh my gosh, I cannot believe I just did that. See, what an embarrassment. Okay. Let's enter from standard in. Thanks, Sherry. Okay, so here's my first word. How about this? How about I do A, B, C, D, E. Okay, so there's 5 letters. And my second word is going to be A, C, B, D, E. So same letters, just shuffled around. So my program should tell us that it's an anagram. All right. I have 4 different solutions. Let's see how long it takes to do. I want to do solution number 1. Okay, that took, what do we got? Tenths, hundredths, thousands, 10,000s, 67 100ths thousandths of a second. That's pretty fast. Solution 2, pretty much roughly the same, just a little slower. Solution 3, just a little bit slower yet. Solution 4. Okay, so this first example looks like those first 2 are pretty close. The last 2 are pretty close, right? If we were writing this for a user, we're talking about a fraction of a second. So any one of these solutions would be just fine. Well, let's play it out. Let's exit with these inputs. Let's put some more inputs in there. I'm not done with the simulation. Oh, no problem. What I'm doing is we're solving a problem. We're solving the problem of determining whether 2 strings are anagrams, meaning that they have the same letters. I've actually developed 4 different solutions, and we're just looking at the performance of each one. I'm not diving into the code. We're not going to do that. We're just looking at which one is better. That's all we're trying to do. So, so if we go, I'm not done with the simulation. I want to do standard in. Okay, let's do this. Let's do A, B, C, D, E. Oh, that was that. 5, F, G, H. What do I got for letters? 1, 2, 3, 4, 5, 6, 7, 8. 9. So let's do 9 letters. And this time I'm going to swap the B and the A and the D and the C. Good enough. E, F, G, H, I. These are 2 strings. Let's see. Solution 1. Oh, still very, very fast. All right. I'm not sure I did 4, did I? Oh, I see what it's saying. Oh, but this 4 is there. Yeah, the output on the screen, something got a little haywire. Let's double check. I know what you're saying there, Sherry, but it actually doesn't. Let's see here. So 1 was really fast. 2 fast. 3. Wow, that was these all look. There's 4. Okay, so 4 all of a sudden is starting to get slow. It's still a fraction of a second. Holy smokes. I'm going to hit 5. I'm not sure why. Oh, I'm still printing. That's funny. See what happens when I get students involved? I had a student modify something in here, and it's actually printing that execution time there. My apologies. Wow. We should do this again, and I should clean up my code. That's right. Here we go. Check this out. We're not done with the simulation. Let's continue doing, let's go up to like, I don't know, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 characters. 1, still fast. 2, still fast. 3, Still pretty fast. 4. So we can talk for a while. And so immediately you start to see that things are getting, actually it is, took 14 seconds. Took 14 seconds to do, and that was just 11. As soon as I go to 12 characters, option 4 takes over 2.5 minutes. Okay. Well, what if, ladies and gentlemen, let's get out of here. I'm going to quit. What if we did the following? I'm going to show you for this talk, we had an abstract that sort of described it, right? That's more than 12 characters, right? In fact, that's 503. Okay. Yeah, I will make sure you guys have the code, and I'll take out that one line that's printing when I choose 5. But anyway, so that's 503 characters. If this is going to take 2 minutes, 2.5 minutes for only 12, I'm not choosing number 4, because number 4, we don't have enough time today for this to finish. Okay, this may not finish before you go to bed tonight if we were to choose number 4. So let's do this. So, free anagram. We're not going to do standard in. We're going to do it from a file. Our first file name is abstract. .txt. Second file name is abstract2.txt, which is the exact same file, but letters mixed around a little bit. All right. Hey, we're still under a second with choice 1. Choice 2, wow, it's still doing it incredibly fast. 3, still incredibly fast. I am not choosing number 4, right? Because we know that's going to take way, way, way too long. Let's exit with these inputs. Let's go with another file. How about this? Standard, no. How about Dr. Seuss's Green Eggs and Ham? The entire book, right? So if we did that, and Green Eggs 2, okay, we just got something that made number 1 over a second to finish it. Number 2, still down in the thousandths of seconds. 3, still down there. Those look really, really good. Again, not doing number 4 because we don't have enough time this week for number 4 to finish. Okay. And just so that you know, oops, I'm gonna Control C and break out of it because I want to show you. I do a word count on green eggs. We're talking about 3,387 characters. And a moment ago, we were going to wait 2.5 minutes just to do 12 with algorithm 4. How about this? Let's do it one more time. How about the entire works of William Shakespeare? All right. So if we look at that as an example for a word count, there is 5,458,199 characters in the entire works of William Shakespeare. Ladies and gentlemen, if we chose algorithm 4, there is not enough time in my lifetime for that to finish. Algorithms matter. Okay, but let's go ahead and See what the others do. By the way, I'm not going to choose number 1 because number 1 takes a really long time also. We're down to 2 and 3, right? We were down to saying, okay, those were actually seem to be pretty efficient. Let's see what we get. So not standard in. Let's go william.txt and william2.txt. And all I did in these 2 text files, I took the very first line of his works and I moved it to the very end in the other file. So they are anagrams if you look at them as an entire string. Number 2, again, we're talking roughly 5.5 million characters. All right. Three seconds. Took only 3 seconds. That's amazing. Let's look at number 3. Basically 2 seconds. 2 seconds to do that. Where some of those other algorithms are horrible. Now you start to see scale of data. All 4 of these algorithms, when we were dealing with like somebody's last name, all 4 of them worked perfect. They were fast, every one of them worked, but now you start dealing with large sets of data. Some of these algorithms come to a grinding halt. So let's look at them and figure out why these things work so poorly. So I'm going to go back to the demonstration, or back to the PowerPoint. So I need to reshare. A window, pick this window. All right, so let's look at these 4 algorithms. Now, before we do, I'm going to just back up a couple slides. Okay, a few slides. You might start to be able to predict where these algorithms are lying on this chart, right? Number 4 was horrible right away, and we stopped using it. So probably number 4 is somewhere around these vertical lines. 1, 2, and 3 worked pretty good, but all of a sudden we took 1 off. Okay. When I say number 4, in our example, in the Python example, number 4 was the 4th algorithm that we were testing. That was the one that we stopped using when we got to 11 characters, let alone we didn't do it in any of the files because it would have just taken too long. Okay, so here we go. Solution number 1 is actually an n-squared algorithm. It was developed as a nested loop. In other words, you basically say for each letter, you then compare for each letter in the other word. So here you got the word Corvette and the word vortique, whatever. So I start with the C, I compare it to every letter. I move to the O, I compare it with every letter. So it is a nested for loop. So I have to walk through all of the letters n-squared times, because for each one, I have to then do another for each. So this was an n-squared. This one hung in there until we started getting really, really sizable data. Then this thing really, really began to tank. Let's look at what solution 2 was. Remember when we got super large, solution 3 was our best solution, but 2 was pretty good. I mean, it wasn't anything poor. 2 was what's called an n log n algorithm. The first thing to do, sort both lists from A to Z, and now just walk down through it and see if you have all the same letters, right? If we took, here, you take the word Corvette, and on both of them, and you sort it, then you get CEEORTTV, and now you literally walk the list. So you have 2 times the n log n. Those are the 2 sorts that you have to do, plus n, because you have to walk the list. Elephant, goldfish. The elephant is the n log n. It's the sorting that takes the time. So the walking the list didn't take hardly any time, so we threw that out. So this has a big O notation of what's called n log n. Pretty good algorithm. Not the best, but pretty close. The next one was actually n. Remember that green line that just gradually sort of moved up in that picture? That's what we were able to achieve. And all we did is walk through the string and simply count how many letters of each. So you walk the strings and you count how many letters. So in this case, you do Corvette, right? There's 0 A's, 0 B's, there's 1 C, and you do that, and then you compare. If you have the same letter counts, then obviously you have an anagram. And so this ends up being 2 to the n, or not 2 to the n, but 2 times n, because I have to walk both lists counting frequencies, plus 26. That plus 26 is because when I'm done, I now have to compare the 26 letters to see if my counts are the same. Elephant, goldfish. The elephant is 2 times n, right? Because remember, I had 5.5 million characters. So 2 times 5.5 million characters plus 26. Again, 26 doesn't matter at that point. And lastly, why was algorithm 4 so bad? This was a factorial. That means I generated every permutation for those letters, and then I literally just went through and I checked to see which one it was. So in the case of a Corvette, in this case, it would generate 40,320 words. If you swap all those letters around, and now I'm checking to see which one it was. So that's just with, what do we have there? 1, 2, 3, 4, 5, 6. That's with 8 letters. Can you imagine what is the factorial of 5.5 million? There isn't enough time to do William Shakespeare. There is truly not enough time in my lifetime to complete it, because the data space is so massive. And so that's why algorithms truly matter. So when we look at these algorithms, for the abstract, there was 509 characters. For green eggs and ham, there was 3,231. And for William Shakespeare, there's roughly 5,333. I took out the spaces. That's why these numbers are a little different than what you saw earlier. This is just pure A through Z's. And then looked at the different algorithms. N log n, how many comparisons you actually have to make to solve the problem. If it's an n squared, how many comparisons you actually have to make. And then if it's an n factorial, for the abstract, the number would be 1,159 digits long. And for green eggs, 9,938 digits long. That's how many comparisons your algorithm would have to make. So at the end of the day, algorithms matter, all right? And as you begin your careers, finding any solution is a great start. But as you develop your skill and you master your craft, finding the best solution is truly the answer. And with that, I guess we'll open it to questions or comments, or back to you, Tech Academy.
It looks like Nemi might have a question. Go for it. Or I'm not sure, maybe that was an accident.
Oh, they're asking about the 26 comparisons. If you think about on that problem, in fact, I can quickly go back to that slide. If you wrote down just A through Z, and then as you walked through like the first whatever it is, Corvette, you would just do tally marks for how many letters you found of those. And then when you're done, you'd have to compare those tally marks for both words. And if they're of equal, then that's where you get the anagram. So that's why the 26 at the end, because there's 26 letters in our alphabet that we had to compare. So, yes, a question. Oh, you were asking. All right.
Yeah, go for it. If you want to chat in the chat box or unmute your mic, however you'd like.
Yeah, good evening.
Good evening.
So my question is, I'm actually new to Python, and then most of all these anagrams that everyone is talking about here today, I'm not actually very good. I'm not actually very familiar with it. So I don't know if you can actually give me a link where I can get to learn this, so it won't be this difficult for me.
We will make available these slides as well as the code that I ran in the background, so that you can see the different algorithms, and so that way, if you're wanting to sort of hand trace them or in fact run them, you could, and so maybe that might give you some assistance. Again, there's a lot of folks I realize that may have been on this presentation that absolutely 100% are just beginning coding. This was not
Okay.
intended to in any way scare you or make you run away. All I was trying to do was to get everybody to realize, as you continue down this road, just because you found a solution does not mean it's the best solution. And that comes with some experience, and by having mentors in not only in this program, but also when you get into your career, having folks that can help you, getting other eyes on what you're doing. So that is the entire intent of this. So I tried not to get too mathy, but this is a tough topic to cover without getting mathy.
Thank you very much.
You are welcome.
Also, I put a link in the chat box if you were looking for a source to know what that means. And also, I think Terrence also give you a brief explanation on it.
Exactly. Thank you very much.
Awesome.
And so, Regina, I will make these available to you, and then you guys can do what you need with them.
Yeah, here's my email, everyone, by the way. Let me know if you guys want the slides, and shoot me an email, and I'll definitely send it over to you. It's Regina at...
That would be preferred from my end as well. Thank you.
Yeah.
Hello, I need a slide, please.
Yes.
Maybe you just send them
me
to
an email to that email I put in the chat box, and I'll send over the slides to you.
I should send an email to this right now, right?
Okay, perfect.
And Priyanka, thank you for your comment. It is one that we can all grow a lot in. I grow every day in this arena.
And it looks like someone raised their hand. Go ahead, feel free to ask the question if you'd like to unmute your mic. Or maybe that was an accident, I'm not sure. Maybe it was an accident. Any other questions? Well, no? All right. Well, I mean, if you do have questions, you can definitely reach out to me. Oh, it looks like, how would you recommend building logic skills for practicing in problems like HackerRank, LeetCode, etc.? It looks like Brooks has a question.
Sure. It's all about practice, right? So if you're looking at a specific thing like the HackerRank, things like that, you need to do similar problems in that arena. There's a lot of resources out there. HackerOne is a great example of a place that you can go that will sort of create some, I'll call it a gym, if you will, right? To work out, in other words, to go and sort of master those skills. As for algorithmic problem solving, puzzles, literally like here's 8 coins, right? What's the minimum number of weightings? Looking for algorithmic puzzles and just constantly brain teasers, problem solving. That's how you really work to get your mind to be looking for different solutions, right? It's not always about code. It's about looking at a problem and what are different ways. Again, the book has been misshelved in the library. How many different ways can you find it? You've got to be able to go at it. So, all right, excellent.
And then it looks like there is one more question. Someone's asking, so they are wanting to get more familiar with algorithms. So they were wondering if there is a specific book that you would recommend.
If you are just beginning development, I might run away from the algorithm books because they're going to be really highly technical and highly mathy if you're at a beginning developer perspective. But I think you could look for just some, literally search for beginner to algorithmic theory, things like that. Because as you saw, we got into logarithms and I was trying to stay out of mathematics. So I just caution you, I love math. So actually I would say go for it, but you may not be as masochistic as me. So that's okay. But yeah, I puzzles are exactly how I would go about it. Just here's a puzzle. How do you do it? I'll give you one more thing. Here's one thing I love to do personally. I love the brain teaser puzzles. The ones that got like nails that are bent and stuff, and you have to physically try to unlink them.
Yes.
I love those. And anytime I can get my hands on those, I'll do them because it really forces you to think. It forces you to think in 3D space, but you have to connect. I see how this is going to go here that I need to use for later, right? In other words, it really helps you work through some problem solving. And now I know some people hate those. They get really, really, really frustrated with them. Your first step is you have to get through that. That's why those types of puzzles I think are awesome. I'll take a developer any day of the week that picks one of those up, and 30 minutes later, I'm like, would you put that down? We need to go to lunch, right? That's who I want. I want something that dives into stuff like that. So anyway, those are just thoughts, I guess. I love it, Sherry. Post pandemic, I'm in.
Also, Nemi, do you have another question? I see that you raised your hand.
If you want to go Mathy, where would you go? Sherry, if you want to go Mathy, just look for a data structures and algorithms textbook. Any of them are awesome out there. And if you're familiar with a particular language, I would add that to your search. So if you are a Java person, data structures and algorithms in Java, data structures and algorithms in C#, that type of thing. That way you're bringing in a language that you understand as you look at these topics.
Awesome. Any other questions? Well, if you do have questions, Rick, do you have a question?
No, I was just going to say with practice and good mentorship, it does get easier and easier. So it's just practice is the key.
And you never truly master it. Keep that in mind.
It's always a learning process, right?
Yep.
Well, there's so many algorithms out there.
Sherry, polymorphism is late binding in the compiler. There you go. That is a short definition.
A brief summary.
And it is beyond the scope of this conversation.
Maybe next talk, I don't know.
There you go.
Great.
We could do polymorphism and inheritance, and that's cool stuff.
Giving you some ideas.
Fundamentals.
All right.
All right. Any other questions? Well, if you do have questions, you can definitely reach out to me, and I can talk to Dr. Brent, and we can figure those questions out and answer them to you guys. Also, like I've mentioned, today's class is recorded. It's going to be posted on our YouTube channel. So let me get all my links in before you guys all leave, so you can check them out in case you guys want to rewatch this video. So here's our Tech Talk playlist. It also has all of our other Tech Talks from previous weeks. I think that got sent perfect. And then also next week, we do have Kyle Rohn talking about the life cycle of a video game. So if you'd like to join, go ahead and check that out. We do also have other Tech Talks already posted on there if you want to RSVP for those, if you're interested in it. Other than that, I'm really glad everyone enjoyed today's Tech Talk, and I'm glad everyone was able to join. Thank you so much, Dr. Brent, for joining us again, and hopefully we'll see you soon. And I hope everyone has a great Friday.
Sounds good. And Sherry, I'll answer your question. Feel free to email me directly if you wish.
All right. Great talk, Dr. Wilson, as always. Thank you very much. And
right.
We will see you soon.
All right. Take care, everyone.
Bye, Doctor.
Bye-bye.
Bye, guys. See you next week.